So what we're going to talk about today is light waves being reflected from surfaces of a thin film, interfering with each other and producing constructive interference and destructive interference, which leads to certain colors being amplified. And an example of this is the beautiful wings of a butterfly. I don't know if you were a kid and you ever kind of, thought butterflies were amazing and you snatched one and you touched its wings and a powder came off on your fingers. And maybe you didn't realize it at the time, but if you looked at the powder on your fingers, it was not the same color as the wing. So the powder on the wings are actually colorless. And so the question is, well, how in the heck do we get the beautiful colors of a butterfly's wings? Well, that powder creates a film on the wings. And depending on how thick or thin that film is, light will interfere with it and produce constructive or destructive interference of certain wavelengths. So, for example, in this blue butterfly here, the dark blue regions, you have a thickness of the film where the wavelength of blue it constructively interferes, okay? So we're going to examine those conditions that create constructive or destructive interference of certain colors. You may need to review Chapter 13, Section 5, and that basically was the first time you were introduced to how interference occurs, and that was in the context of sound waves, and it applies the same criteria applies to light waves as well. And what that criteria had to do with how the waves added up, right? So if you have two waves and they line up, so the peaks line up on top of the other peaks, right? You're going to have constructive interference. And the amplitude of that wave added together is going to be twice as big as the two, right? As each of the individual ones. Now, the second situation you can have is destructive interference, and that's when the peaks and the valleys don't line up. And so what you get is it adds to zero. So, right, if this is like plus A and this is at minus A, well, they're going to add up to zero, right? And then if these occur at zero, well, 0 plus 0 is 0. Okay, right? Negative A plus A is 0. So when you add these two together, you're going to get a net 0. Well, I can't move it because of how I layered it on top of that other image there. But you get the idea, right? When they add up together, they're going to cancel out. Okay, so what you get is like a flat line. So that's destructive interference. So just kind of remember that. Can't spell today. Destructive interference. Okay. So let's see how that relates to thin films. So we're going to be considering, white light is made up of all the different wavelengths, right? Well, we're just going to kind of pick one wavelength at a time when we talk about interference from a thin film. So we're going to consider one color at a time, and whether or not that color constructively interferes with itself or destructively interferes with itself, okay? And then the first film we're going to look at, so notice how we are talking about thin film 1, okay? So we're going to look at two different types of thin films. The first thin film we're going to look at is a transparent one, okay? And behind the transparent film, you have an opaque film. So thin film 1 is going to be a thin film that is transparent on top of an opaque backing. Okay, So here is a schematic of that situation. So here we have air, right, with index of refraction N1. And then we have our material, our thin film, index of refraction N2. And then here we have the opaque backing and its index of refraction. It doesn't really matter, but it's so big that the light does not penetrate through it, okay? So let's shine some light on that film. Monochromatic light. So we're going to shine light of a single wavelength. And what's going to happen is, well, it's going to bounce off of the top of that film. But you know what? Some of it is going to go into the film as well, right? As we know, there's going to be reflection and refraction every time light strikes something. And because this is a transparent film, light will definitely refract into it, right? So we're going to have that light wave also refract into it. And it's going to hit the bottom of this film, which is on the top of the opaque surface, and it's going to bounce right back out. And then it's going to kind of refract again when it gets back into the new index of refraction N1. So both of these are going to happen at the same time. So here in this picture, we have them layered on top of each other. So the first one bounces off the top of the film. The second one bounces off the back of the film. And so what you have is these two light waves right here moving parallel to each other, and they're going to either constructively interfere or destructively interfere. So what conditions are going to make it either constructive or destructive? That's what we're going to find out. So a single light wave that was incident on the thin film has now been split into two outgoing waves, okay? And those waves have traveled different paths, right? They've traveled different distances. This one only traveled this distance, and this one traveled a little bit longer, right? A little bit deeper, went farther in before it came back out. So we're going to compare the distances that each of these light waves have traveled. So these two light waves were in phase before they encountered the thin film. And that's because they were a part of the same incident wave. But in general, two reflected waves are not in phase when they recombine, okay, on the top of the film. And that's because when light enters the film and reflects off of the back surface, right, the part that's up against the opaque, well, it travels farther. And so it has the chance of its phase ending up in a slightly different place because it traveled farther. And so whether interference occurs that is constructive or destructive, it's going to depend on the number of wave cycles that fit into that extra distance, okay? So to get constructive interference, the number of wave cycles that fit into that extra distance should be an integer, okay? And if that extra distance adds up to some integer number of wavelengths, well, then those two outgoing rays are going to constructively interfere, and we're going to see a bright reflection of that color. Destructive interference occurs when that distance, that extra distance, is equal to an odd number of half cycles. So odd number of half means 1 half, 3 halves, 5 halves, 7 halves, okay? Not 2 halves, right? Because that would be 1, not 4 halves, because that would be 2, right? That would be constructive. So it has to be an odd number of half cycles. And so when the distance, the extra distance traveled equals odd number of half cycles, well, then those light waves are going to be out of phase. Okay? So then that color, whatever that color is that's going in, is going to appear dark. It's not going to be bright. It's going to be dark. We're not going to see that color. It's going to be kind of like dimmed out. Okay? So when we consider that this light is normal to the surface, okay, it strikes the surface of the film face on, then we can easily calculate the path length difference, okay? We can ignore the fact that it was at a slight angle. So like what I mean is, right here's the opaque part. You know how in the picture it looked like that? Okay. right? We can assume that this is simply equal to, if this is the thickness of the film, we can assume that that path length difference is equal to 2 times the thickness, okay? And we can ignore the fact that it's at like slight angle. So when we assume that the path length difference is equal to 2 times the thickness of the film, then we can set up the constructive and destructive interference conditions. So here's a picture that shows both of them together. And on the blue side, the blue highlight, constructive interference, light green highlight, destructive interference. And what we have not taken into account is the fact that the wavelength changes when it enters a new index of refraction, right? So we can write these interference conditions in terms of 2 different wavelengths, either the vacuum wavelength or the wavelength in N1 or the wavelength in N2. And so what you'll notice here is that these conditions are written in terms of lambda 2, which is the wavelength in index 2, which is the thin film, okay? And you can go back and forth, right? Because remember, we know the equation that describes the wavelength of light depending on what medium it's in. Go back to, I think it was section 1 or 2 of this chapter that told us that. So these are all written in terms of lambda 2, the wavelength in the thin film. And these are the exact same equation, but we just moved n over, okay, so that it looks a little bit nicer. All right, these are both the same equation, just n moved over for one of them. And same for this, okay? So here's the destructive or constructive conditions here, destructive conditions on the right. And so depending on how much extra path length that the light has traveled, we could get constructive or destructive. If it adds up to an integer number of wavelengths, constructive. A odd half, integer, destructive. And this is how we write an odd half integer. If we write it this way, we're always going to get an odd number. So, oh, well, look, I put the equation right here, didn't I? I must have forgotten, right? So the equations up here are written in terms of lambda 2, which is the wavelengths, the value of the wavelength in medium 2, okay, in the thin film. But if, for example, maybe in the problem you were given the vacuum wavelength, well, then to use this equation, you would need to figure out what lambda 2 is, and you can easily do that right here, right? So lambda 2 would be the vacuum wavelength divided by the index of refraction of 2, medium 2, okay? So here are those written out, just kind of what I just did there. And if you don't have the vacuum wavelength and you just have wavelength 1 and wavelength 2, right? Let's say the outside is water and then the thin film is made of glass. Well, you can just relate them like this, okay? Where N1 would be the index of refraction of the water, and then N2 would be the glass. Okay, so it doesn't have to just be air and glass or anything like that, right? It can be any 2 medium. So we can then rewrite those equations in the figure in terms of lambda 2, which is already been done, right, in the figure. So we can find the minimum thickness. So the next thing we're going to do, so right, this is going to be, right, this is going to give us like all the different interference indices. So the question is, how can we find the minimum thickness for each interference condition? And the minimum thickness would occur at the integer m equals 1. So if we plug in m equals 1 for both of these equations, we can find the minimum thickness. Okay? The minimum thickness required to achieve constructive interference or to achieve destructive interference for a particular wavelength. So if you notice, these equations are written in terms of lambda 1. Okay? So you just feel comfortable flip-flopping between lambda 1 and lambda 2 as necessary. And lambda 1 is, of course, right, the wavelength in the outside portion, and then lambda 2 would be the wavelength in the film itself. So there's some, these are kind of duplicated, right? These are in the figure. So there's not like a million equations. I kind of just duplicated them here because they also appeared in that figure. So let's do an example. Okay. So in this example, the film is soap, okay? And it's on a bathroom tile. And so we have monochromatic light. So it's a wavelength of 560 nanometers. And it's initially in air. So our N1 will be air. And it strikes a layer of soapy water. And so our film is going to be the soapy water. That'll be N2. And the index of refraction of that film is 1.4. And it's on a bathroom tile, which we know that tile is opaque, right? So this is working with film 1, thin film 1 with an opaque backing. And so if the layer of soapy water is 700 nanometers thick, does constructive interference occur, destructive interference occur, or does neither occur? And part B is, what is the minimum thickness? So if we don't know if constructive or destructive interference is going to occur. So let's set up both equations and plug in our knowns. Okay. So for constructive interference, we have 2 times the thickness equals integer multiple of wavelength in that thickness, right, in that film. And if we want, we could rewrite this in terms of the wavelength in lambda 1, okay, by using this equation right here. So what were we given? We were actually given the wavelength in 1, right? So if we were to use this equation here and we were to put 560 for lambda 2, we would not get the right answer. So I rewrote it in terms of lambda 1. And so for destructive, let's go ahead and write the destructive condition, and then we'll work them both out. So 2 times the thickness, right, that's the path length difference, is going to equal 2m minus 1 over 2. That's the odd half cycle, or odd half integer, times lambda 2. And we can rewrite that in terms of lambda 1, like so. N1 lambda 1 over N2, right? Because lambda 2 equals N1 lambda 1 over N2. Okay. So let's go ahead and work on the constructive side now. So our thickness is 700 nanometers. So twice the thickness is going to be 1400 nanometers. So that's our left-hand side. And then the right-hand side, since we're given lambda 1, we'll go ahead and fill in everything. We don't know what m is. We want to see if m is an integer, because if m is an integer, then we know we have constructive interference, right? So let's find out if m is going to be an integer with the information provided. N1, the index of refraction of air. Lambda 1, the wavelength of the light in air. And then divided by the index of refraction of the film. So when I calculate all that, what I get is 400 times m. And so the question is, well, is 400 times m is m going to be some integer if I set it equal to 1400 nanometers? So let's find out. Okay, the left-hand side, 1400, equals the right-hand side, m times 400, and m ends up being 3.5. So that is not an integer. So we know that constructive interference does not occur. And so, well, we can right off the bat, we know it's destructive interference. But we did have a third option, right? Neither. So neither would be if this number came out to like 3.75, right? Because that's not a half integer of anything. But let's go ahead and go through the math and just kind of verify, right? So now if we do destructive interference conditions, so twice the thickness was 1400 nanometers. And we're going to solve for m, see what we get. Okay, same kind of right-hand side over here. And so we get the 400 again, so we're going to divide. And the question is there an m that satisfies this equation here? So let's find out. 1400 divided by 400, well, that equals 3.5. And is there an integer m that satisfies that equation? Yes, that's m equals 4. Right, so m is always an integer. Right, I know we're working in the destructive interference condition, and you're like, okay, wait, why are we solving for an integer? M is always an integer, but we do all this stuff around m, right, to turn it into a odd half integer, right? So if we find an integer that fits nicely, well, then we know it's definitely for sure destructive interference. If m came out to like 3.5, then we know it's not destructive either, right? Because then this equation would not be satisfied if m came out to like something that wasn't an integer. So we know it's destructive interference. And now that we know it's destructive interference, we go back to part B. What's the minimum thickness? Well, we need to use the minimum thickness equation for destructive interference, right? So we pull that from the previous slide. In terms of lambda 1, so that would be n1 lambda 1 over 4 times n2. Plug in all of our values, and you get 100 nanometers. So that's how like the thinnest the film could be in order to get destructive interference of this color light, 560 nanometers. Okay, so let's talk about another type of film. So just as a reminder, thin film 1 was a transparent film on top of an opaque surface, like a floor, right? Something where light cannot penetrate. But what if now you are, having a great time over the summer and you're blowing bubbles, right? And you take the bubble wand and you notice that you have some, interesting color effects going on. Well, what's on either side of this soapy film? It's air and air, right? It's not a soapy film on the floor. It's a soapy film in air. So both sides of the film are air. And so that's the second type of thin film. There is no opaque backing, okay? Air is on both sides, or the same index of refraction on both sides. And then even more generally, it could just be any index of refraction that is less than this one. That's written here. Okay. So let's talk about what happens now. So we have the same situation. So light will bounce off of the top end of the film, and then some of that light will refract inside, bounce off the back of the film, okay? But this time, since there is no opaque backing, there is going to be no phase shift that occurs. And so what that does is that changes the interference conditions, okay? It changes the interference conditions. And now they're actually flopped from thin film 1, okay? So now the odd number of half integers gives us the constructive interference condition. And the integer number of wavelengths gives us the destructive interference condition. Okay, so when you are dealing with a thin film with a smaller index of refraction than the film itself on the outside, okay, then the conditions flip from the opaque backing case. Okay, so compare these two figures and you'll see that clearly. And that's because there is no phase shift when the light reflects off of the back surface, because the waves that travel through medium 2 or through medium 3 are going to travel faster, so they don't have this phase shift. Okay. So now when you're doing these thin film problems, the first thing you need to recognize is, are we talking about thin film 1 or thin film 2? Okay, are we talking about opaque backing or non-opaque backing? And then you choose the constructive or destructive interference conditions. So now when we do this example, obviously we're going to be using the second set of conditions, right? Where we have a thin film that has a lower index of refraction above and below the film. But in a test or something, you may not know. You'll have to read the question to know, okay? So we have glass and it's on an LCD display. And we coat a lot of different things in anti-reflective coating to minimize the glare. And so what we want to figure out is, if we apply this coating to glass, and this coating is called zirconium acrylate, and it has an index of refraction of 1.54, then what is the minimum thickness needed for that to accomplish a reduction in reflection? Right? We want to reduce reflection. So what does that mean? We want to know the destructive interference condition, right? Because we don't want that wavelength to reflect brightly. We want it to be diminished. We are trying to reduce the glare. So we are going to be looking at destructive interference. And that's determined by reading the problem and seeing that we are interested in a reduction of the light. Okay? So again, we're talking about light with a wavelength of 560 nanometers in air. And the index of refraction of zirconium acrylate is 1.54, and then we have air on top, and down below we have glass, okay? And so it's not air and air, it's air and glass, but that's okay because the index of refraction of glass is smaller than the thin film. So it satisfies the conditions for thin film 2. Okay, where the backing is not opaque. So we're going to use destructive interference because we want to minimize the reflections. And we want to find the minimum thickness. So we're going to solve for d min. And the destructive interference condition for this situation is going to be the same as the constructive for the first thin film 1, right? But you know, if we're not ready to go flip back and forth between the two, you just scroll up and make sure you're looking at thin film 2, where the backing, right, or the backing and 3 has a smaller index of refraction than the thin film. And so this is going to be our guy right here. We're interested in destructive interference, so we're going to use this equation right here, either one of these. Okay, and then this is in terms of lambda 2, so we're going to have to convert lambda 2 to lambda 1, which we know how to do. So let's go ahead and write down that destructive interference condition. Two times the thickness, m lambda 2. Lambda 2 is n1 lambda 1 over n2. And so we're solving for sorry, I wrote d min. D min, sorry, I copied the wrong one. Here we go. D min for constructive. So we do need to go up here because I didn't write them again for the other film, right? I only wrote them for thin film 1. So we're going to pull this equation from thin film 1, which is going to be the constructive one because they're flipped. And it's right here. So d min, well, d min is just when m equals 1, right? So this would be fine. D min would be this dmin for m equals 1, which would just simply be equal to n1 lambda 1 over n2. So n1 is air, lambda 1 is 560, n2 is 1.54, and so we get 363.6 nanometers. So that's going to be the minimum thickness for destructive interference on thin film 2, which is the thin film, which is our coating, has the highest index of refraction than what's above and below it. Okay? So get comfortable like reading through the problem, identifying, are we talking about thin film 1? Are we talking about thin film 2? And you have the constructive and destructive conditions written down for both types of films and for both wavelengths. Okay? So to wrap up this section, we now know that light waves can interfere constructively or destructively when they go through a film, right? And reflect off of the front end of the film and the back end of the film. And depending on if this is thin film 1 or thin film 2, you're going to have a constructive or destructive interference, okay? And that depends on how many light cycles equal the thickness, twice the thickness of the film. So we can also get interference when we shine light through two narrow parallel slits. This is called the double slit diffraction experiment. It's pretty interesting. So the double slit experiment is a pivotal experiment in optics, and we're going to send in light of a single wavelength, okay? So that has one lambda. It's not white light that has a whole bunch of wavelengths. We're going to send it through two narrow slits. And what you might expect to see is just two bars of light on the other side, okay? But if those slits are small enough, okay, separated by a distance d that's really, really small, that is similar to the wavelength, well, you actually get a totally different pattern. You don't just get two rectangles. What you get is an interference pattern where you have bright regions separated by dark regions, okay? The bright regions are going to represent constructive interference, and the dark regions or the dark fringes are going to represent destructive interference. And so let's look at the geometry and see how can we figure out what the constructive and destructive interference conditions are. So to understand why this happens, we can go back to Huygens' principle. And recall Huygens' principle states that the source of light, as it spreads through space, each wavefront can act as a new infinite number of sources, right? So if we send in light, okay, shining through these two slits, some of it goes through these slits, right? The rest of it doesn't go through these walls. Well, then these two slits act as sources of light, okay, that create these circular wavefronts. And then this circular wavefront spreads out and acts as another source that creates this one, that creates this one, okay? And so then light from each of those slits, they're going to interfere wherever they overlap. And where they overlap, you could have the peaks adding up to the peaks and getting constructive interference, or you could have the peaks adding to the troughs and getting you destructive interference. And where we care about that is we place a screen, and where those two light waves cross each other on the screen, that's where we're going to be able to see if it's constructive or destructive. And so where these light, the green, the blue and the red meet, will give us constructive here, maximum, maximum, maximum. And where they don't line up, you're going to get your minimums, you're going to get your dark fringes. Okay? So at certain locations on the screen, you'll get interference maxima, and then in certain locations on the screen, you'll get interference minima, and that anywhere else, you know, is just going to be kind of like a mixture of the two. So it'll be kind of like not super bright, not super dark. So we call this double slit interference pattern, okay? And this is such an important experiment because this pattern that we saw is conclusive evidence that light is indeed a wave. It has wave properties. So let's now look at how these interference conditions are figured out. There's a little bit of geometry here. This picture just kind of explains how it's found. You can certainly just take the equation I'm going to show you at face value. You don't have to rederive this, okay? But this is how it's found out. So the conditions for constructive and destructive interference, well, it's still going to be the same idea as before, right? The path length difference will be a whole number of wavelengths for constructive. And the path length difference will be an odd number of half wavelengths for destructive. And the path length difference, which is this purple piece right here, okay, ends up being equal to d sine theta, just by using right triangle trig. So we can combine this as the left-hand side, right? The path length difference is a whole number or a half number. We combine that with the path length difference from geometry being d sine theta to get the constructive and destructive interference conditions. And so for constructive interference for the double slit experiment, d sine theta, where d is the distance between the two slits, it's going to be an integer multiple of the wavelength. For destructive interference, d sine theta is going to be a half integer multiple of the wavelength. Okay? Similar idea as thin film interference, except our geometry is just a little bit different. So now when we look at the integers m, these m's are going to tell us which fringe we're talking about. So in thin film interference, the m wasn't super important, right? But here in double slit interference, the m is going to refer to a particular location on the screen. And so it's important to understand what m means in double slit interference. So m equals 0 is going to give us the central bright fringe, okay? And so the m's in double slit interference are going to track which fringe we're on and whether it's the dark fringe or the light fringe, okay? So if we look at the constructive interference condition and substitute m equals 0, well then what is that going to give us? That's going to give us our central bright fringe. Because if m equals 0, well then d sine theta equals 0, and sine of an angle that equals 0, well, that angle must be 0, right? And so if we come back to this picture up here, this angle 0 is going to refer to the normal, right? If theta equals 0, then this red line is on the normal and going straight across, which would be on the screen straight across, right? Right here in the central bright fringe. So m equals 0 for the constructive interference condition gives us the center of the interference pattern. So the center of the interference pattern. So for other bright fringes, for example, +1 or -1, well, that's going to give us the next set, okay? And that theta will tell us this angle right here, the theta that makes that true. Okay, so we talked about the bright fringes. What about the dark fringes? Well, if you plug in m equals 0 into the dark fringe equation, the destructive interference condition, it does not correspond to the center of the pattern, right? It's going to correspond to the first dark fringe. And that dark fringe happens at half a wavelength, right? If we plug m equals 0, what we get is 1/2. And if we solve for theta, well, that's not going to give us theta equals 0, right? That's going to give us an actual value for theta, which is going to be like this angle, you know, or that angle. Okay, so m equals 0 for the destructive interference does not give us the central bright fringe. Instead, m equals 0 for the dark fringe is in between m equals 0 bright and m plus 1 bright. So this guy right here is where we're going to call m equals 0 dark. Okay, we're going to place it right here. Okay. And then m1 dark would be here. And then m minus 1 dark would be right here. And you can find those by just solving for the angle, right? If you get an angle that's positive, well, then it's going to be m plus 1. If you get an angle that's negative, it'll be m minus 1, right? Because negative angles go down this way, positive angles go up this way. So locating the maxima and minima, right? We can rewrite those equations and just move the d over. And that way we're just solving for theta, right? And if we know the location of theta, then we can find where those fringes are occurring, because that theta is going to be just this guy right here that creates a right triangle, right? Where this would be the m equals 0 bright, and then this would be whichever one we're locating. The theta that gives us, you know, whichever one we're locating there. So what you also notice from these two equations is the dependence on wavelength. So if we increase wavelength, then sine theta gets larger as well, and thus theta gets larger. So what does that mean in terms of the pattern? That means the pattern gets broader, okay? So what do we mean by broader? These kind of bright spots get like wider, okay? They're not like super sharp. So now what if the slit spacing is increased? Well, it's inversely proportional to the angle, right? So if you increase the slit spacing, then sine theta gets smaller and theta gets smaller. And then in that case, the entire interference pattern becomes narrower and sharper. Okay, so you don't have these big blurry bright spots, you have a much sharper bright spot. So let's do an example using double slit interference. So let's say that we send light from a laser through two narrow slits, and the slit spacing is 0.1 millimeters, so that's D. And we're producing an interference pattern on a screen that's 5 meters away, so that'll be L. And the angle from the central bright fringe to the next bright fringe is 0.3 degrees. So the central bright fringe, remember, is m equals 0. And then the next one would be either m equals 1 or m equals plus 1 or minus 1. Okay, and this would be theta. So the question is, what's the wavelength of the light? Well, since we're talking about bright fringes, we know we're going to need to use the constructive interference condition. Okay, d sine theta equals m lambda. So if we want to find lambda, then using the m equals 0 is not going to help us because we're going to be multiplying 0 by lambda. We can't solve for lambda here. So we want to use the m equals 1 condition, and we know the angle, okay, because it was told to us in so many words. So we know theta, we know d, and we can certainly figure out sine of theta, so we can solve for lambda quite easily. This is a schematic of what the picture or what the text is explaining, okay? And right, the screen is 5 meters away. Here is the central bright fringe, and at this angle, 0.3 degrees, is where m equals 1 bright fringe is, okay? So if we plug in all of our values, we find that the wavelength is 524 nanometers. So that's part A. That's lambda. Part B, what is the distance on the screen from the center of the interference pattern to the first dark fringe? Okay, so the distance that we're looking for is going to be from this point right here to wherever the first dark fringe occurs, okay? And you might remember from our discussion earlier that the first dark fringe occurs right here. So, I'm sorry, right there, right here. I drew the picture. So here's the picture, right? So here's our double slits separated by distance d. Here's our central line, and this is the length of the distance that the screen is away from the slits, which is 5 meters. And the first dark fringe occurs between m equals 0 bright and m equals 1 bright. So we want to find this angle. And if we find that angle, well, then we can find this distance, right? Because this is a right triangle right here. So if we know this, we can find this, right? Because we know this side. So we're going to use the destructive interference condition to find theta. And we know that m here is going to equal 0 because we're talking about the first dark fringe, which occurs at m equals 0. And we have d, we have m, we now have lambda from part A. So let's find our angle theta. So we can do that by solving for theta, inverse sine of 1/2 lambda over d, right? I just solved for theta. Solve for theta from here, and then what you get is 0.15 degrees. So the triangle that we're going to use, right, is this one right here. The height of the triangle is what we're looking for. What we just found was the angle. We know this, the base of the triangle, 5, so we have everything we need to find this side of the triangle. And I think the best way to do it is to use tangent, right? Tangent is opposite over adjacent equals tan theta. So tangent of 0.15 degrees. Okay, I lost my black. There you are. Just wanted to write that a little bit better, right? Tangent of 0.15 degrees is going to give us the opposite over the adjacent. So we can solve for the distance. That becomes tan of 0.15 degrees times 5 meters. It's going to give us the distance, which is 0.013 meters. Okay, so for double slit interference, you want to draw a picture. That's going to help you. Okay, you want to draw a picture like this. And so it's not just about the constructive or destructive interference equations. You're going to want to draw the picture as well, and it's going to help you. And then you're going to want to remember that m equals 0 bright fringe is at the center. Okay? And then visualize these right triangles. Right? This is a right triangle. Okay? And that's going to help you solve for whatever you need to solve for. So in this got the concept, and we'll wrap up this section. We're going to talk about the double slit experiment, and we're going to talk about the m equals 3 bright fringe. It's located at an angle of 0.5 degree from the central bright fringe, and if we were to change some parameters, how could we cause the m equals 2 bright fringe to appear at 0.5 instead of the m equals 3? So since we're talking about bright fringe, we're going to use the constructive interference equation, okay? So the constructive interference equation is, remember, d sine theta equals m lambda. So let's see, what are the factors we're changing? So, so the original equation was the m equals 3 fringe, right? And being located at 0.5 degrees. So if we increase the slit spacing by a factor of 3/2 and not change the wavelength, is it possible to get theta at 0.5 degrees? So let's compare that to, so this is the equation we're going to compare everything to, right? After we manipulate lambda and manipulate d, we should be able to get this equation back. And if we do, then we know that theta will come out to be 0.5. Does that make sense? So let's look at part A. So we're going to increase the slit spacing by 3/2. So we're going to multiply d by 3/2. And we are not going to change the wavelength. So if we multiply d by 3/2 and we leave the wavelength, I wrote a 2 here. Why did I write a 2 here? Oh, because we want the, sorry, I'm like, I wrote this just a little bit ago, right? Because we're trying to get the m equals 2 bright fringe to be located at 0.5, right? So that's why there's a 2 for m here. So the question is, if we multiply this by 3/2, can we get this equation back? Well, let's move this over, okay? So what happens is we get d sine theta equals 4/3 lambda. And does d sine theta equals 4/3 lambda look like this? No, it does not, right? So we won't be getting the same theta if we were to solve for theta. What about part B? So we decrease the slit spacing by 2/3 and leave the wavelength unchanged. So now we're going to multiply d by 2/3. Okay, we want our m to be 2 because we want that theta to equal 0.5 with m equals 2 there. And so, well, now if we kind of rearrange to solve for d sine theta, what do we get on the right-hand side? We actually get 3 lambda back. So that's a go. Part C, follow the same procedure. We're going to be increasing the wavelength by 3/2 and not changing d. So the equation we're going to write is d sine theta equals 3/2 times our m times lambda, because what we're changing is the lambda, right? So just because I wrote the 3/2 over here doesn't mean I'm not multiplying lambda by 3/2. I just wrote it to the left of m. So now when I kind of simplify this, what I get is 6/2, and 6/2 is 3. So I get the same equation back, and I know that when I solve for theta, I'll get 0.5 degrees back. Follow the same procedure, okay, for part D and E on your own. And you'll see that you don't get theta equals 0.5. You don't get the same expression back, okay? So to wrap up this section, we looked at interference in another geometry. We still used monochromatic light, which is light of a single wavelength, but this time, instead of shining it into a film, we shined it into 2 slits that are separated by a small distance d. And what we saw is when we looked at a screen behind those 2 slits, we saw an interference pattern. So we saw bright regions, we saw dark regions, right? And using some geometry, we found the equations for constructive and destructive interference for the double slit experiment. So the final thing we're going to talk about is diffraction. So diffraction is the spreading of light after it passes through a narrow opening. So before we talk about a narrow opening, let's talk about what light does when it is shown through a wide opening. For example, like a flashlight through a door, okay? So we can use Huygens principle to understand what happens when we do this with a narrow opening, and we can also understand how it applies to a wide opening. But for a wide opening, it's kind of a moot point. And what you see is that for a wide opening, what you end up with is if you were to put a screen here, you would get a beam of light that matches the same width as the opening, right? So these are the planar wave fronts, okay, going through this opening. And remember, they're all going to act as little individual sources. And then when they spread out and hit a screen or a wall, what you're going to see is you're just going to see the outline of the doorway, right? If you're shining a flashlight through a doorway, you're just going to see on the wall on the other side of the doorway, you're just going to see like a rectangular beam of light, right? So, however, when that opening is narrow, we're going to actually get the bright and the dark fringes again, okay? So now the opening is narrow. And what is it? What do we mean by narrow? We mean that the opening is roughly the same size or smaller than the wavelength of the light that we're sending through, okay? So because the opening is narrow and it's really close to the wavelength of light, only a few of the wavelets are going to go through, okay? Like one, like right here. Okay, compare that to this picture where like a whole bunch went through. And we got this kind of flat, right? All these added up to a maximum. Well, now when we only let one through, what happens is the wavefront, this is acting as a single source, and then we're going to see the wavefronts expanding and expanding. And this light is going to start spreading out, which is what we call diffraction. And the waves are going to kind of like leak out and give us a pattern. So here we can visualize this using water. So if we make a wavelength of water by pushing on the water, and the ripples are going to denote the wavelength of the water. If this opening is much bigger than this wavelength, right? Well, we're just going to see like a big flat wave crest, okay? This is kind of like the doorway, the flashlight through the doorway example. But now when the opening is small and it's pretty close to the wavelength size, we're going to see this circular wavefront form, okay? And by the time they get to the edge, to wherever they're going to hit, we're going to see a pattern. Diffraction becomes important when the width is comparable to the wavelength, the width of the single slit. And we can write diffraction, anything that behaves like a wave, we can talk about diffraction. So we can talk about water waves. We can also talk about sound waves. So if a door is shut, a door is open and you can hear someone talking in the other room, well, let's think about why that is. Well, the wavelength of sound that comes from human voices is roughly 4 feet to 13 feet. And a doorway is roughly 3 feet wide, so it's comparable, right? And therefore, the sound is going to go through and spread out, okay, in all directions. And we can hear the voice, okay, even if we're like all the way over here from the door. Whereas if we were standing right here, you see those waves are not going to reach us with such a strong amplitude because you can see they kind of fade off as they get to the side here. But if the wavelength is comparable to the opening, well, then these waves are going to spread out in the circular wavefront pattern, and they're going to diffract. So let's talk about diffraction, the single slit diffraction experiment. So it's going to be set up in a similar way as the double slit. Okay, we're going to have the single slit now. We're going to send the waves through, and we're going to have a screen on the other side. And that screen will be some distance L away. And then the pattern you're going to see is the single slit diffraction pattern. And it looks, kind of similar to the double slit, right? We have bright fringes and we have dark fringes. But the diffraction or the interference conditions are going to be a little bit different. So again, we're going to call the dark fringes diffraction minima. Okay, instead of interference minima, they're diffraction minima, and then the bright fringes are diffraction maxima. So a different physical reason for these patterns, right? In the double slit experiment, it was due to interference of two different waves. And in diffraction, it's due to one wave. So how do we calculate the locations of the maxima and minima? So here's our little geometry set up, and I'm going to spare you the derivation here. So we can calculate the path length difference, and when we do that, the path length difference ends up being equal to W sine theta. But what we see is that the dark fringes are going to be equal to integer number of wavelengths. Okay, we move for single slit diffraction, we move the W, instead of calling it D, we call it W for the width of the single slit. And then we write it on the right-hand side just to keep from getting confused with double slit, okay? Because they kind of have the same form. If you were to move the W over here, it would have the same form, right? As the double slit, except it's kind of having the switch like in the thin films, right? The dark fringes, so the destructive interference condition is going to look like the constructive interference condition for double slit. So the integer number of wavelengths is going to give us the destructive condition for double slit diffraction. And what we're going to be tracking is the dark fringes, right? So the difference between double slit and single slit, it's very important to know the differences. It's very common to get them confused because their equations look very similar. And then you also get a similar pattern on the screen, right? The essential difference is for double slit, the pattern is caused by light waves from one slit interfering with the other. And in the single slit, it's the light wave interferes or diffracts with itself. So in this example, we are using a green laser pointer, so it has a wavelength of 532. We're going to shine it through a slit that is 1.5 microns wide, and 1 micron is 10 to the minus 6 meters. We want to find the angles of the first, second, and third dark fringes, okay? And so this equation here tracks the dark fringes, right? This is the constructive interference or the dark fringes of the pattern, okay? Destructive interference. So we want to find the first, second, and third. So the first dark fringe is m equals 1. We know the wavelength. We know the width of the single slit. We can easily find theta here, right? Pretty straightforward. It's going to occur at 20.8 degrees. We can find m equals 2 pretty easily, right? It's going to be equal to 45.18 degrees. But what about the third dark fringe? Put that in the calculator. You're going to get undefined. What does that mean? Well, what that means is that the third dark fringe is not visible on the screen, okay? The width that we chose in comparison to the wavelength is stretching out the diffraction pattern, and so we don't get the third dark fringe. This one here, the third dark fringe, 1, 2, 3, the third one is going to be like off the screen somewhere, okay? That's what that means. So with the width chosen and the wavelength, there is no dark fringe, okay, before the end of the pattern. And that has to do with the relative size of the single slit and lambda. So let's compare them, right? Lambda is 532. 1.5 times 10 to the minus 6 meters. If we convert that to nanometers, that's 1,500 nanometers, which is pretty, which is a lot bigger than 532, right? So if we want to get more fringes on the screen, we need to have a narrower slit, okay? So let's talk about the intensity of the single slit diffraction, right? So what we're looking at here is how bright the bright fringes are and the location of the dark fringes. So when you have a slit width that is roughly the same size as the wavelength, what you see is, if this is from negative 30 to 30, what you're going to see is a really spread out diffraction, okay? And when you increase the slit, you will start to get more diffraction pattern. Further increasing will get you even more diffraction patterns, right? More dark fringes will appear. So the larger the slit width, the more dark fringes you'll observe. So using this idea, let's compare these 3 diffraction patterns. Okay, and can we look at these and kind of like see these figures, right? Look at A, one big peak matches this, one matches A here, one big peak, right? And then C kind of has like a big peak and then a smaller and then a little bit smaller, right? So that one may be more like B. And then this B on this side has several, which would look more like C. Okay, so that's how this 2D graph is interpreted in the actual screen photo of the diffraction pattern. So with that in mind, order them from widest slit to narrowest slit. So the widest slit would have more dark fringes, okay? So B would be the widest, followed by C, and then A, okay? And so to wrap up this section, waves that pass through a narrow opening, a single slit diffraction, they spread out, and we call that spreading out diffract, okay? And diffraction becomes a prominent effect when the size of the opening is small, meaning it's close to the wavelength size. And waves, diffraction pattern created by waves passing through the narrow slit, they have the bright and the dark fringes, just like in the double slit diffraction. And the positions of them depend on the relative size of the wavelength and the slit width, like we just did in this, got the concept and looked at in this figure. Okay, so I'm going to stop here. There's one more section, 23.9. I'm going to just cancel that section. It's diffraction through a circular opening, okay? It has similar effects But we just, there's just not enough time to cover every single aspect. So I'm going to drop off 23.9, okay? So let me know if you have any questions.